Hey guys, it's OpenQuant here, and today we have question number 11, 2D Grid Game 2. So this is an extension of a previous problem on our channel called 2D Grid Game. And if you haven't yet solved that, I highly recommend it, as it would make the entire process of understanding this problem much more easy to follow. So in this problem we have the exact same setup. We have our 6x6 grid and our character starting at 1, 1. He or she can only move down or right. Except now in this game there are two power-ups located at 2, 3 and 4, 6. The question asks how many possible paths exist such that our character can reach the final destination 6, 6, such that it collects at least one of these two power-ups. As usual, let's start with a little illustration. So we have our 6x6 grid. Excuse me. So there's our grid, 1, 2, 3, 4, 5. Straighten this out a bit. Okay. 1, 2, 3, 4, 5. And again, this grid is one index, so the starting position right there is 1, 1, and we end at 6, 6. So 2, 3, 4, 5, 6, 3, 4, 5, 6. So we have two power-ups located at 2, 3. So row 2, column 3. We're going to use gold to just indicate the power-up. And the second one is at 4, 6. Row 4, column 6. The question asks how many ways can we start from the beginning, we use a red dot, and get to the end 6, 6, such that we go through at least one of these two power-ups. And again, one of these two power-ups implies that going through both power-ups is also a valid path. Let's go through some potential examples to help illustrate what we need to count. So starting from 1, 1, we could go this way, and we're hitting that power-up right there. Could go through. That's another valid path. In this case, we're going through that power-up right there. And another example that goes through both power-ups would be like this. We go through both power-ups starting from the beginning and ending at 6, 6. So the question asks us to count the number of valid ways such as that the ones we just illustrated. Alright guys, now we'll actually begin to count the number of ways we can reach our valid solutions. So we will split we'll split our count into two distinct cases, to two cases. The first is where we go through this power-up, and the second where we go through the second power-up. So number ways through, we'll call this just 2, 3, the first power-up right there. So to calculate this amount, we can take the number of ways to get from here to there. And once we have that number of ways, it could be like that, it could be like this, it could be like that. Once we have that number of ways, we then compute the number of ways to get from here to our final destination. And by multiplying these two numbers together, we get the total number of ways to get from our start to our end going through the first power-up. Okay, I'm just going to erase all of these little dots now. Okay, great. And the reason this logic makes sense is that for each path from here to there, whatever that path may end up being, it can have any of the potential paths from here to there as its predecessor, as its starting path. And by multiplying those two values together, it's as if we're choosing combinations of socks or of clothing, in a very generic, typical probability problem. So now let's begin to compute this value. So again, this is where knowledge of part 1 of this problem comes in handy. So to compute the number of ways to get from here to there, we simply sum the total number of steps, and from that choose how many of them are going to be rightward steps and how many are going to be down. So in 3 steps total, we can get from our start to our end in this case. So our total original value will be 3 in this case. So we're going to have 3 total steps to choose from. And of those 3, we have to select either 2 of them to be right or 1 of them to be down. So it could be 3 choose 1 or 3 choose 2. And we know that these 2 values are identical. So now we have to compute the number of ways in our second path, which is from here to the finish line, 6, 6. So again, there are how many total steps? 1, 2, 3, 4, 5, 6, 7. So 7, and of those 7, 1, 2, 3, 4, let's see. Of those 7, we have 1, 2, 3, 4 going down. So it could be 7 choose 4, or again 1, 2, 3, or 7 choose 3. So this product, I'm just gonna pick the expression with the smaller term, just to make it, I guess, to make the numbers look more appealing, although it has absolutely no bearing on our final calculation. So the total number of ways to get from 1, 1 to 6, 6 through this power up right there is equal to 3, 1 times 7, 3 choose 1 times 7 choose 3. Now let's repeat the process for the second power up, which is right there. And now that we've kind of internalized the concept and the very basic process to solving this subproblem, we can just kind of, we'll go through a little faster. So the number of ways through, in this case, it's 4, 6. So we have our first expression, which is getting from here to there. So we have 1, 2, 3, 4, 5. So that will be our bottom of the choose term. 6, 7, 8. There's 8 total steps, and 5 of them are rightwards movements. So just for brevity, it's also equal to 8 choose 3. And we multiply this term by the number of ways to get from here to our destination, which actually, just looking at this game, we can tell it's 1 because we can only move down or right. However, there are no rightwards movements. So we have either 2 choose 2 or 2 choose 0. In both cases, it's equal to 1. So this whole expression then reduces to 8 choose 3. Great, so we can just, I guess, sum these 2 values together, right? That one right there and that one right there, and we have our total number of ways, right? I mean, sounds good. Let's close up shop, ace the quant interview. Not so fast, actually, because we need to consider that the number of ways through this first power up that we counted, some of those ways actually go through this second power up right there. Guys, I apologize for all the annotations on this grid. I'm feeling a little lazy and I don't want to erase all of them for like the 5th time. So anyways, what I was saying is that in our original count of going through this first power up right there, we actually counted number of ways that we go through the second power up, which is a valid solution. So, no harm, no foul, right? But in our second computation, this one right there, where we calculate the number of ways that goes through the second power up, we also included in that count the number of ways that goes through the first power up. So we're doing a little double counting in this example. In this case, we're double counting the number of ways that goes through both the first power up and the second power up. And just to kind of like relate this to probability and to counting, this is actually has to do with the inclusion-exclusion principle, where we have the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Except in this case, instead of probabilities, we're counting the number of ways. And in this case, this would be our A and this would be our B. We're trying to find, again, the number of ways that we go through at least one power up. So this is where that or comes from, at least one. This is the number of ways through 2, 3, the number of ways through 4, 6, and this is the number of ways through both. So to get our final solution, to get that expression right there, we actually want to take these two values, so 3 choose 1, 7 choose 3, so this is our A term, add the 8 choose 3 term, that's right there, and then subtract the number of ways that go through both power-ups. That would be our A and B term right there. So to do that, we can just use the exact same process. Okay, it looks like I will actually have to erase stuff, which is not a big deal, it's fine. So as I was saying, to compute the number of ways through both power-ups, we can actually just do the exact same process as we did for the first two subproblems. However, instead of just two terms, instead of just being the first and the second term, there will actually be 3 terms. The number of ways to get from here to there, the number of ways to get from there to there, the first power-up to the second power-up, and the number of ways to get from the second power-up to the finish line. So let's do that. I'm just going to write it up here. So number of ways through both is equal to, so the number of ways from the start to the first power-up, which we know is 3, 1, or excuse me, 3 choose 1. The number of ways from the first power-up to the second power-up, which we can compute to be, again, 1, 2, 3, 4, 5. 5 choose 3. And the number of ways from the second power-up to the finish, which we know is 1. I'll just write 2 choose 2 because there's 2 steps and 2 of them have to be down. So that is our number of ways through both power-ups, and this is the value that we need to subtract from our expression. So let's copy this right here. Okay, great. So now we have our total expression, which, this right here is our final solution. There's no more games now. I promise that this is our final solution. And yeah, thank you for sitting in on this problem. I hope everything made sense. If it didn't, please leave a comment. And also, if you haven't taken a look at part 1, I highly recommend doing that, just to understand more about this intuition, where we're choosing the number of ways to get from one starting point to the other. Thank you for listening.